An implicit equation is an equation that has x and y on the same side of the equation. So a good example can be given by x squared minus 2xy minus y is equals to 4. Okay, now in this particular example, it's actually possible for us to rearrange it so that y becomes an implicit function of x, right? So in other words, we can make y the subject. However, such a solution of y in terms of x is not always possible. Like if I look at another implicit equation, let's say we've got x cubed y squared plus y cubed is equals to 5. In this particular example, it's not possible for us to express y directly in terms of x. However, if we assume that y is a differentiable function of x, we can still find the derivative by differentiating each member of the equation implicitly. So the idea of implicit differentiation can be thought of as an extension of chain rule. If I'm to give a brief example right now, okay, let's say we want to differentiate y squared. Okay, so if I want to differentiate y squared with respect to x, we can't differentiate this straight away because we're differentiating with respect to the variable x and we've got y squared here. So we can't just go, let's take the 2 down and subtract 1 away from the power and let's call the result 2y because that's differentiating the result with respect to y. So now what we need to take note of is let's assume that y is a function of x. Okay, so x and y are related. So we're going to assume that y is a function of x. And the idea behind this is if I can't differentiate y squared with respect to x, then I'm going to take this notation and I'm going to rewrite it. So now instead of differentiating y squared with respect to x, I think about what I can differentiate y squared with respect to, which is y. So I'm going to rewrite this as d dy y squared. But you know that if I write it like this, I'm obviously changing what I'm looking for. So I'm going to undo the change that I just made, which is the fact that I wrote a dy at the bottom. So I'm going to add a dy to the top up here. And then see how I have a dx in the bottom originally? I'm just going to add a dx there. So the idea here is that this is chain rule. Okay, d dy y squared times dy dx should be the same as d dx y squared. And the idea is that dy in the bottom here and dy in the top here, they cancel each other out mentally. Now, we never cross these out, okay? But at the top of our mind, we can pretend that these two cancels, leaving us with d dx y squared. So take note that we never cross these two out. So never during the middle of exam or during your practice or anything like that, actually cross the dy in the bottom out here and dy at the top here. Okay, that's very fundamental. But if I rewrite it in this form, we can see that if I now look at d dy y squared, that's just going to become 2y, and then I'm going to multiply dy dx at the end, and this is the derivative of y squared with respect to x. Now, this at first might be extremely weird, okay, but it's actually not that bad because if I bring out a specific example, right, like if I say that y is equals to x squared plus 3x, right, and I want to differentiate y squared, okay? So now if I want to differentiate y squared, we're differentiating x squared plus 3x all squared. And if I'm doing that, this is literally just chain rule. So if I apply the chain rule on this thing, what I get is 2 times x squared plus 3x to the power of 1. And then at the back, we multiply by 2x plus 3. And this is exactly what I have on the left, right? So if this was y squared, okay, we got 2 out of the front, and then this part here becomes the y. And this part here, the 2x plus 3, is the derivative of y, isn't it? So we call this dy dx. So 2 comes down to the front, we subtracted 1 away from the power, and then we've multiplied the end by the derivative of my function. So this is literally just the chain rule. The only reason why we're calling this implicit differentiation is we don't actually know what y is. Okay, if we know what y is, then this is just standard chain rule. So this is what implicit differentiation is about. It's when we want to differentiate y or whatever other variable we have, okay, and we know that y is a function of x. This is a very important assumption, right? So y is related to x, and now if I want to differentiate, I just apply chain rule and I write it in notation form. Okay, so implicit differentiation is weird because we're not used to the notation, but it's actually not that bad. So that being said, we are just going to take note that when we're differentiating implicit equations, okay, we're just going to stick to the normal rules of differentiation. So stuff like chain rule, product rule, quotient rule, they're all essentially applied at the same time to differentiate whatever expression which we have. And it is important to take note that x and y are not constant, okay, and that y must be considered as a function of x. Now, I'm going to do a lot more numerical example until we kind of get the idea behind implicit differentiation. And I'm just going to make a note that implicit differentiation is not necessary if you're just looking for Extension 1 math. Okay, some schools might teach implicit differentiation as part of Extension 1 math as an extension topic, right? An extension for Extension 1 topic means that most schools will not assess implicit differentiation as part of the Extension 1 course. So this is literally extra work. But for those of us who are going to do Extension 2 math, this is quite necessary. Okay, so take note of whether you want to review this section or in how much depth you want to look at this section and stuff like that. Okay, either way, it would be a good idea just to have a rough idea of it. And of course, if you're doing Extension 2, make sure you practice up on it and you can actually do this. Right, so that being said, let's look at some numerical examples.